last time I attempted to give a framework into which you could put the impact of correlation into continuum models in a structured way. And good, Adam showed up. He's not terribly late. Let the record denote that my student showed up for my talk. Okay. And so today I just want to go back through this framework and apply it to a very, I guess I'd call it toy. You probably never heard of it, the Stockmeyer model. I sort of thought it out myself, and then I looked and I found it. Okay, it does exist. It's called the Stockmeyer model for polar solvents. And so I'd like to go through the whole BBGKY and the continuum limit, the hydrodynamic limit for this model, and show you what comes up and show you the structure of the equation. And if it's too much math or I'm not lighting you up, punchlines on slide 41. That's pretty much almost where I stopped. So not too far to go, and I'm going to stop when I'm done, and I may stop early, I hope. And then we can basically discuss what we would do with this model. And of course, you would want to improve it, but also what questions you'd hope to ask. Okay, so just to remind people who don't maybe do chemistry that water is a non-spherical object. That's one of its endearing features. Carbon dioxide is also non-spherical. That's why it's such a greenhouse gas. Water is also a very good greenhouse gas, right? Maybe even more than carbon dioxide. And it's also quite strongly, relatively strongly charged, makes it an excellent solvent. So it's got a net charge, oxygen and hydrogen, but there's two hydrogens, so it's like, sort of this little, it's a dipole. It's an excellent example of a dipole. And I'd like to fix a domain then and do some sort of molecular dynamics, and then do write down a very simple Hamiltonian for a molecular dynamic system, and then do a sort of BBGKY hierarchy, just skip down to some of the results and say, here's what it looks like, here's the continuum limit, and then here's what happens if we take the continuum limit straight from BBGKY, and here's where the interesting terms come in. So to get okay, let's see if I can remember correctly. The top one is the wrist only. And be careful, the wrist only. Oh, it is very sensitive. You have a lot of coffee. It's a little Brownian motion. Okay, so I've got positions. Xi are the positions. So I'm going to replace this thing over here with a vector. There's a xi plus, or I guess minus is probably the negative, and xi plus is down here. So each xi is really 2 points. The negative part of the water and the positive part. And so xi without the plus or minus is the center, that little corner in there. And then you have a length L, which is how far apart they are. And it might be written here, I don't know. Mass, okay, I don't think so. And then d of theta is just a fixed function. It's just cosine theta, sine theta. It's just a vector. So you might notice I'm doing this in 2 dimensions because I just want to absolutely minimize all the notation. So I'm just going to play my little math game in a 2-dimensional world. Extending to 3 dimensions is not hard, but it's just why. I want to get an idea across, and that's not the idea. And then Q is the total partial charge. So I have a minus Q up here and a plus Q here. So I've combined these 2 hydrogens. You could, of course, split these off into 3 vectors, and you could make this 3 points and then have one here with different charges. It's not a hard extension. It's just more notation, and I'm trying to minimize notation. So you could think of a sort of charge density. It's just the sum of, you have, say, delta functions at all the xi pluses minus delta functions at all the xi minuses with a common total charge. So net charge is 0. So I just got a big collection of 0 net charge dipoles filling up space, and I want to take limits of this and see if I can get something intelligent out of it, and particularly understand how higher correlations would fit into continuum ideas. So if you want to think about this at a continuum limit, you can say, well, there is an electric potential, psi, which I'm in vacuum. So epsilon naught is my free space dielectric, and I've got some sort of total charge Qn, which is my distribution of all these charges. And you can solve this with the Green's function. So I want to be on a periodic domain. I don't want all my water to evaporate, so I'm going to put it in a small little region. That would be very bad in my water. So I'm going to put it in a fixed domain, and I'm going to take G is always going to be the Green's function for the Laplacian on a small periodic domain. And OK, it's very natural to say, oh, hey, look, I've got two. And in fact, I have to admit, this is really a full circle for me. When I was a freshman physics student, they gave me this problem where you have a dipole moment, and you had to calculate the electric field far away. And I'm like, I've got a function. I'm evaluating it at one point and evaluating it at another point that's nearby. How could you systematically expand that? That doesn't make any sense. There's no, and I thought all night about, I stayed up all night about this, trying to create the Taylor expansion. Because it's not obvious at all. If your function's not smooth, there's no Taylor expansion. You have to understand that smoothness gives you this beautiful dichotomy. Whenever I see this, I still have that chill up my spine. I must be so stupid that I don't know how to do this. So, OK, but now I know how to do it, so I kind of feel a little bit smarter. OK, so you got the Green's function at 2 points nearby, and I'm going to just Taylor expand it. And basically, what I'm getting with my little dipole moments is a stencil for the Green's function. I'm going to stencil and evaluate my Green's function at a stencil. And so L is the spacing. It's relatively small. But one of the fun things when you do a real problem is that you got to decide, how am I going to scale this thing? The scaling is really far from obvious. And so L is a small parameter, but so is Q. The charge on an electron is small. So is the mass of an electron. So you got three incomparable small things. Who's smaller than who? You know, well, what units? OK, so this is just my, and here comes out your dipole vector, because the dipole vector is what separates these two parts of the water molecule. And so if I plug this expansion in for Qn and sum over all these guys, I get my electric field. I invert the Laplacian. I get the Green's function at these different points, dot with this dipole, I guess this dipole vector, what I call it. And you get QL over epsilon naught. Comes out quite naturally. And so you say, OK, I now have an electric potential energy. If I know psi, I know how to compute this. You can run through a very similar guy. You get one more derivative, and you get this sort of, OK, mathematically, this is the Hessian, not the Laplacian. So another place, that generates a matrix. So this is now a Nablus squared of G is a matrix. It's the Hessian matrix. It's not the trace. And so that is a matrix, and it's a little bilinear form. So D and that T up there is not time, it's transpose. So that's D transpose. And I try to take them out, but I guess I didn't get them all because last time it looked like time evaluation. OK, so this is an interesting sort of, I have a stencil, which comes from the way I broke this is basically my stenciling of this Hessian for electrostatic potential. I would say this is not a good approximation when things get very close together, but I'll address that. I'm really thinking about moderately far apart particles, not colliding together. That's a completely different game. OK, and so I just want to say Rij is, of course, just the matrix, the vector of differences, not the norm. And grad square is the Hessian. OK, so I think I hit this button. And OK, here's my caveat. Yeah, short-range forces, that you really shouldn't use this. If I really want to make a model and implement it, I wouldn't just use this term, because that's a really crazy, doing that approximation is a crazy way to get the interactions when two particles come close together and slam into each other. So if another molecule comes within comes within the length of the dipole, it's not a very good model. And you want to do something quite different. You want to have another short-range term in here, which is quite singular, but in a nice sort of rational way, and maybe has some sort of angle dependence. So B is like some inner particle thing where you have a relative angle orientation between two guys and some sort of force. And this probably ought to be completely repulsive, right? Otherwise, my dipoles are all going to glom together like little magnets. And that's not what they're going to do either. So there's a lot of electronic structure in the middle that I've completely abused. OK, so you ought to do this, but I'm not going to do it because I want to really focus on the longer range part. And this just is going to be sitting along on every page, and I don't want to rewrite it, and it just takes up space. So I don't need it. It's not the focus. But yes, of course, I should do something more intelligent. If I was going to actually try and make a molecular dynamic model out of this, it's such a bad model, you probably wouldn't do it anyways. Okay, but now immediately, if you want to make a Hamiltonian, you really have to treat the momentum in a more honest way. You can't just do, so you got a mass and you got an angular momentum. So you got I is the, what's it called? The moment of angular momentum. I can't remember what I is called, but it's ml squared over 4. And it's much smaller than the mass. So in fact, these are much easier, small things are much easier to rotate than they are to move, right? The rotation becomes, so this is going to be very quick. You're going to get a fast, slow system out of this. You're going to have 2 time scales immediately when you have small, spinnable objects. And so I have this electrostatic term, I have this short range guy that I'm going to drop on the next slide, and then I've got 2 scalings for my momentum. Okay. And I should say that this was partially motivated, at least. Alexei Konashev is speaking on Wednesday, right? We just put his name on this. That's part of the reason why I said, yeah, we got to bring him. I put him on my slide. So, okay. And he has a sort of beautiful title, Non-Local Dielectric Response of Water in Nano Confinement. That sounds like a great, I hope that's what he's going to speak about, but I don't know. Okay, so, and of course you have to make a few adjustments. He has a polarization field that's really going to be the coarse graining of my D. So that's sort of the idea. It's kind of part of what got me thinking about this. Okay. So, okay, I'm just going to go through the formalism now. I don't know how long it's going to take me. Maybe not very long at all. I think we could be done. We could have a long coffee break or a long discussion. Okay, so I'm going to put down my n-particle Hamiltonian ODE, my molecular dynamic system. The xi's, the positions, are just trundled along by their momentum, which is their velocity when you divide by the mass. And the angles are trundled along by their angular momentum, which is just the angular velocity, omega I, when I divide by the whatever the moment of angular inertia. I don't know what I is called formally. Okay, that's trivial. This part's more fun. How do the velocities change? Well, I get this third derivative, this 3 tensor of the Green's function. You might say, oh, that's going to be really singular. I would say when r is 0, I could just smooth out the Green's function. I don't care about the singularity. Because when r is small, then I should be using this term over here that I'm going to drop anyways. And I have to be careful. If I get too close to the screen, it doesn't know where I'm pointing. Okay, so this is kind of fun. Okay. But I'm going to drop this term, which I think is red over there. I'm a little bit colorblind. I think that's red. Okay. And then this omega is a square. And now the bot here is rotation by pi over 2. So this is the vector rotated by pi over 2, the dipole vector. And that's just the transpose. So that's like a little bilinear form. It's a matrix, vector, vector. But this vector is rotated first. This is a okay, I knew I was going to do this. Okay, but no, don't bring up your mail. Fortunately, my mail is very boring. I learned as chair that my mail is so boring that if I bring it up, nothing bad happens. But okay, yeah, okay, don't go to the top of the screen. That's the method. Okay, so this is like a 3 tensor dot dot. So this is like a vector. So this is a vector equals vector. That makes sense. And this is scalar equals scalar. But this is an interesting sort of little structure. Okay, so it's all. But these are going to be my fixed, how to say this properly, functions against which I'm going to project my probability density. And so this is what's determined. This is theta and r are all sort of my independent variables, and this is a fixed function. And I'm just going to project against this to get the flow probability. So in fact, I'm going to record that what f super x is this guy up here, and f super theta is this guy, is the second one here, and these guys. And one of the big differences is the scaling. This is L squared. This is much, the x is much smaller. So this is much bigger. This guy, because if you divide, I think I divided by m and I here to get here. So when I divide, I divide this by m and this by I is much smaller, so this guy gets much bigger. So this guy looks slow, right? This is fast, basically. If I scale these guys, scale out the masses. This guy's getting really pushed strongly. This guy's not. And so if I'm going to go to equilibrium, this guy's going to get there way, way, way before. So really, it's a fast, slow system. Quasi-adiabatic, if you want to think of it that way. But of course, it's Hamiltonian, so okay, it's not going to really relax in quite the same way as a damped system. Okay, so what does the BBGKY hierarchy give me if I want to take marginals of this system? I'm just going to go through the sort of results. So I'm going to first, as I advertise, I'm going to drop the short-range terms because they just clutter up my page. I don't really care what they're doing. They're not the story. I want the sort of quasi-longer range interactions, the dipole moments and things. So the Liouville equation for the n particle distribution is the evolution of the scalar probability density, scalar. Z is Z1's the n particles in R, 6n. So I'm in 2D, but I've got 3 sets of variables. That's right. I think that's right. Well, oh, yeah, 2 are scalar. That's right. Two-dimensional, no. X and V are two-dimensional. Theta and omega are one-dimensional. 1, 2, 3, 4, 5, 6. OK. And so Z with the bar is these time traces. So these are what these particles are doing in this 6n dimensional space as a function of time. And then the probability density that I want, if I plug in one of these traces, is I'm thinking that it would be a delta function, right? Or a sum of many delta functions. I thought I changed that notation. Anyway, OK. This is like the delta function at this point Z bar. OK, maybe I have an old version of this. Maybe I may have grabbed the wrong version of this, in which case I'm going to switch it out before I get to the end. OK, so when I project this one, the evolution now of the velocities and the angular momentum is this probability distribution projected onto these fixed functions. That's very, it seems trivial. Maybe it is obvious to everyone. It wasn't obvious to me, and that really is very unifying. I just have a density, and I project it onto 2 fixed functions, and that gives me my evolution. That's the time evolution. And so I'm just reminding you that this is what I'm projecting onto. Theta and x's are independent variables, and I'm just integrating over the thetas and the x's. And the only difference here is that one has got L squared and one doesn't. So one is quite a bit scale different than the other. And so the flux of probability, well, the velocity changes your position. Omega changes your angle. And these guys, fx and f theta, change your linear velocity and your angular velocity. So that's what's making the probability flux around. And so that's my flux function. And then I multiply by my density. And that's my conservation law is the divergence of that guy. That's Liouville's equation. Really that simple. There's my conservation law. And if you write it out a bit more explicitly, you get this sort of, because the divergences all come out in a nice way. So you could probably even simplify these a little bit more. These divergences could be simplified, I think. But OK, you get a nice, simple conservation law in 4 variables, xi, theta I, vi, and omega I. And specifically, if you go down to the one marginal, I'm going to spare you the fun details. The one marginal, you get this, what I was calling this 2-particle convolution, because this is it's not really convolution, it's an integral over many variables, but I could maybe try and draw it, but it's a little bit even tricky to draw a picture for how you're convolving. But you have this sort of 2-particle convolution, which comes very much from the fact that my original system is 2-body interaction. I've got, I look at my neighbor, it's a sum of pairwise interactions. And so you basically get something almost completely, this trivial transport of Fn1 coupled to this divergence of the 2 marginal. And unhappily, you get an n minus 1. You don't divide by n because I didn't scale it right. Say, OK, well, if I take n to infinity, that kind of looks ugly. So why don't I rescale it? And that's sort of the first interesting question. If I want to rescale, there's a lot of ways to do it. And when you're taking a system and you're trying to push it to a scaling limit, you're really saying that there's a whole continuum of problems. And the problem I'm looking at sits somewhere on this continuum as n goes to infinity. And it just happens to be that Q is small, and M is small, and L is small. But they're all living on some curve, maybe. And as the curve goes to infinity, I have some behavior. But which curve am I on? Well, there's a lot of curves you could be on. I'm just going to pick one just to make my life simple. I'm going to scale Q squared over Q is small, M is small. I'm going to take this guy small. I'm going to take the charge, what's the word, smaller. Well, Q is small, M, it should be small. So maybe Q is 1 over n, M is 1 over n. OK, and then I get 1 over n. OK, it's a game. And of course, Q is finite. Q is fixed. M is fixed in this world. And so I'm sort of giving you some sort of scaling, some small parameter. OK, I'm going to just then fix L. So I'm going to make the charge small, the mass small, fix L, not scale it, rescale my forces by 1 over n, and then I get a 1 over n out here. So now I'm back into sort of what I would think would be a mean field limit regime. At least it makes some sense now to take n to infinity out here, right? But you can see that particularly when you have multiple parameters, multiple small quantities, it's not an intuitive thing how to get back to the mean field scaling. And so now if you take a formally, a Vlasov style mean field equation, n to infinity, this becomes a 2 tensor of some f, which is really the one marginal. So the one marginal becomes f, and then this becomes these 2-point correlations break down to just classical convolutions. These two particle, what I call these 2-point convolution, break down to a classical convolution. And now you get a mean field sort of guy. And now that would be what I would say, what I would hope. And in fact, I tried a little while with Ving. I think Ving might be here. We tried a little while to prove this mean field limit, and we weren't able to apply the standard tricks to do it. So it probably doesn't have one. We couldn't fit it into the classical way. But let's say we did have a mean field limit. Could we understand physically what's happening? Could we take particularly a continuum, a hydrodynamic limit of it? And so you can take your macroscopic variables. What are the things I don't care about? I don't really want to think about the particle velocities. I don't really want to think about the angle of every particle, and I don't want to think about its angular velocity. So I'm going to integrate out these 4 variables and define these sort of marginals. Z tilde is the things I'm integrating out of. And so the density is a function of position and time, but not these other variables. And I integrate out the first marginal, the marginal against the velocity, the marginal against the dipole angle. So this is the average density-weighted displacement field and a density-weighted macroscopic dipole angular velocity. Okay, and if you've not seen these before, it's kind of interesting. If you see before, this is completely sort of standard electric response. Okay, so you have a charge density sigma. You gotta think about it for a second. It's really conditional. You can think of it, it's a little bit trickier, the macroscopic version of this. It's a conditional probability on position and angle, right? If I have I want to know what's the probability that a charge is at a certain position here? Well, I should go a distance L/2 away. And I say, well, I've got a molecule here, and okay, now I draw my molecule pretty big. The dipole, I'll draw the dipole like a little cigar. There's the positive part, and there's the negative part. Or it could be over here, and maybe there's the negative part, right? And there's the positive part. So what's the probability that the center is here and the angle is what it needs to be? Well, you can write it out as a little integral, conditional integral over the angle. I'll spare you the analysis, but there's a small difference. Again, you do a little simple approximation, and you can re-identify this as one of our buddies, rho d. This integral becomes rho d. And so the charge density is just some constants times the divergence of the displacement, which is fairly classical. Okay, so I have a Poisson equation that should look, the Laplace of the potential is just the divergence of the displacement field. That's fairly classical. The electric field is then the gradient of psi is this guy here. Okay. Okay, so you get back what you would like to have. That's what you would write down if you just said, this is my system. Okay, and the electric potential, the energy, I think I might have called it curly E sub b, but here I'll call it U sub b. The gradient phi squared is just this sort of familiar, that's also a classical formula. So in the mean field, you get a bunch of classical formulas back out. So, okay, that's good. If I want to take the hydrodynamic limit from Vlasov, then I integrate out all these fast variables. And so there's my Vlasov system. I've got this sort of scalar now, or what do you call the one? I don't know, the one marginal, this Vlasov density, solving this Vlasov system. And I just project it against these 4 moments, right? You can always project against higher moments, and there's a whole field of trying to close models projecting against higher moments. But I'm just going to look at these four moments. And share the details. You get a continuum equation for the density. You get a sort of an Euler-type velocity equation with a pressure term and a source term, although I want to assure you can write this as a conservation law. This can be written as a divergence of a Reynolds stress Roman assured me of that this morning, so that's good. That's not conservation law. It just doesn't look like one. Okay, this is a bit more interesting. What happens to the displacement? You get a pressure, you get a convection term, and then you get this sort of rotational term here, rho omega d bot, so rotated. So the angular velocity is rotating you. So d bot, the d is the vector, so the bot acts on the d, and it's just rotating you. So that's a rotational thing. So the other terms are 0, are just saying, if rho is constant, and this is just saying the angular velocity is rotating d. Okay, that sort of makes sense. And then the interesting part is what happens to the angular velocity. Well, there's this extra term out here. There's actually sort of source term, the interaction of this guy with this sort of stencil from the Green's function, and some more familiar sort of divergence terms. And of course, there's 4 pressures, which you have to figure out what you want to do if you want to close your system. But I would, again, my intuition is that this is not what is driving stochastic effects in the system. That this is a restoring force that is not inducing, in fact, anything is fighting stochasticity. This is sort of a mollifying. These are generally viewed as regularizing terms, but you have a flavor of 4 of them, but you can't trivially express these in terms of the moments here. You gotta find a closure model for these. You have to decide what you want to do if you want to close the system. Taking them to be 0 is not unusual. Okay, it's not the only way, but it's not. I thought for a second I might want to derive these right-hand side terms where they come from, but I think probably the appetite for looking at my integration is probably low. So I'll just say that you can, if they're in the slides, if you're curious how the integration goes. It's quite hard to follow all the notation, the tildes, and the integration gets a little optically confusing. But basically, you get these cubic 3 tensor and 2 tensor terms pretty standardly. It's pretty standard. Okay, it's not hard. And they're in the notes if you want to see them. Okay, so what's the punchline? Oh, yeah, I'm doing great. Half an hour. I think we'll be done quick here, unless there's a long discussion. Okay, so now I want to take the hydrodynamic limit of this first marginal. I don't want to go to the mean field limit because I don't think there is a mean field limit. I think it's not a mean field problem. And so I want to take this limit, and I want to understand the structure of the problem that comes out. So what do I have? I've got this, the equation for the first marginal is this coupling to the second marginal, its divergence through two variables, through Hessian and third gradient, so 3 tensor of the Green's function coupled to the displacement and integrated with these scaled guys. So it is, I think, helpful to introduce what I call the second marginal residual, which is the 2 marginal. I sort of simplified notation up here, dropped the ends. The 2 marginal minus the tensor product of the 1 marginal. And if I'm correlated, that's not 0. That's where all the correlation lives. And so I can write this as a perturbed Vlasov system. And if you go back and read some of the original papers of BB, that's exactly what they did. This is how they would write these, as a sort of thinking of these terms as corrections to the lower order terms. That was the initial thought. And so this sort of correlation term sits, so I get a Vlasov because I've added it back in, and then I subtract it out, and I get this correlation term, which is then this sort of, I should think of this, I'll rewrite it as a 2-point correlation of a vector. There's a vector. Here's another vector with a 3 tensor. And so you've got a bunch of vectors. It's already looking, well, we'll see in the end. It becomes sort of a cubic sort of scaling to it. It looks cubic in the unknowns. Okay, so that's my correlation term, but it fits in here. If I think that this is the term which is driving stochastic perturbations, fluctuations in the system, it fits inside here. It gets mollified by this sort of kernel. And it enters into the equation not in a haphazard way, but in a very functional way. So what comes out when I look at this, the continuum limit of the first marginal, well, if I knew the second marginal, this is the exact system. I have no approximation. I've gone from my molecular dynamic system to this system with no approximation if I knew what this term was. Okay, continuum equation. That's obvious. That's familiar. Sort of fluid flow, Eulerian. Of course, in our problem, the average velocity may be very small, so U could be 0. Okay, and then I get a source term, but also this sort of stochastic term that is this There's a double colon here because this is a, let's see if I have to get this right, that's a vector. This is a 3 tensor, that's a 2 tensor. No, there's a D out here. There's a vector there, a vector here, and a 3 tensor here. So it's a double contraction of a, is that right? Is that? No, he doesn't. No, this guy's a 2 tensor. So this is a double contraction of a 3 and a 2 tensor. So it gives me a vector back. Okay, the displacement satisfies a pretty simple equation. I'm going to simplify it on the next slide. This is actually, if you set these to be 0, it's pretty simple. And this is maybe the most interesting one. It's the evolution of the angular velocity. It has a source term in here from the last one, but also this stochastic term. And here D2 is sort of what we'd like to be able to predict. It maps R4. It's got 4 variables left after I've integrated it out. Right? It's got a function of these two positions into a 2 by 2 matrix. It's a displacement vector. And it is the integral. Can I move this guy around now? I think I have to get him out of the way without hurting anything. No. Why is it not working? Is it this one? It's that one. There you go. Okay, that one, get him out of the way. All right, it's the tensor product of these 2 dipole vectors at 2 different locations, integrated against this sort of residual correlation, the 2 marginal minus the tensor product of the 1 marginal, and integrated over the rest of the variables. And so this is the thing that you would like to be able to understand if I wanted to understand this sort of impact of at least 2 particle correlation on the electrostatic structure of this undrinkable water. This is certainly toxic water. Okay, so that's the system. It's a beautiful, to me, PDE with some unknown terms in there that I'd like to fit. If I want to think of it as a stochastic PDE, I put these terms in here, and then I mollify them a little bit. That's a convolution. That's interesting. I have to mollify it, and they fit in the structure. And that's what I would claim is the sort of systematic, I wouldn't say rigorous, systematic derivation of a stochastic impact of a correlation on something that has a dipole vector. And there's a couple of, this is not the right slide. Somehow I grabbed the wrong version. Let's get out of here. I don't know how I did that. Maybe I didn't save it. All right, I went to the wrong place. Okay, I'll just open this up. This is the up-to-date version anyways, just to save myself the time. Last slide. Okay, is that big enough? That's big enough. I can make it a little bit bigger. No, I didn't get much bigger. Over here? Over there maybe. Plus, zoom in. There you go. Okay, good enough for me. Okay, this is the slide I really wanted to update. Okay, so how do you understand this system? Okay, as a mathematician, I go look at it and go, that's really sort of it's too many terms. So let's just simplify just let's look at special cases. So let's take this guy now small so that I can drop the source terms in the U equation. If you remember, what am I dropping? I'm saying, well, look, here's I think this is the guy. Here's an L squared term here. So there's no L here. There's L here. This is the fast system. That's the slow system. So let's just make it 0. Let's just make this term 0. But then let's do even more. Let's just make U 0 as well. So let's take all the pressures to be 0. I don't really want to think about them. Let's take the velocity. I'm not thinking about my water as, I'm not stirring this glass. It's an electrode. The water has, the average velocities are probably quite small. They're just sitting there mostly. What I care about is maybe I'm messing with the electric field. Maybe I'm forcing the electric field. There's no ions in here. There's no electrode yet. But at least I have this guy respond. So it makes sense to set this to 0, set the density to be constant, say, set the velocity to be 0. What's left over? Does it all just disappear? Does it become trivial? No, it doesn't. It becomes a sort of odd system. I really thought about it, looked this while, and it kind of hurts it's a little bit odd. I get okay, this is just what the angular velocity does to the dipole. It rotates it, right? That says my time derivative of my displacement is the orthogonal to my angular velocity. My angular velocity rotates me around, right? It rotates me around the circle. That's just rotation. This is a wave equation. If you make it a constant, that's a wave equation. So that's a little second-order wave equation for the displacement, and it's forced. I had to rewrite a little bit, but I did it 4 times, so I'm pretty sure I got it right. And so this is already interesting. This is cubic. This is d D is an unknown. There's D bar. That's cube. So that's linear. So you get this D to minus D symmetry. You get this convolution, the two-point convolution of this guy with this orthogonal guy. And here's your stochastic terms over there. So it's sort of a funky little, basically a wave-type equation with this stochastic noise in here. So this is unforced, and maybe if there's no, maybe this would go to 0. I don't quite know. There's no damping in here is the only problem. So the energy has to be conserved. So, but you could imagine throwing in a bit of damping for some reason, because it's not a perfect Hamiltonian system. It's, you know, the molecules are absorbing energy somehow. They're not. You know, the collisions are inelastic or something. You know, so you could add in a little bit of damping, and then you would go down to some sort of limiting case. But okay, that's sort of the structure of the problem. It's a noisily forced wave equation, which I don't quite understand this source term. I don't have an intuition for it yet, but okay. Okay, and the other thing you could do that would make a lot of sense is to come back to your original system and basically put in a fixed charge density, but give it a sort of, you know, the easiest thing to do. Rather than putting an electrode, is this natural to put in a fixed set of charges that don't move and don't interact with anybody? They just generate an electric field. So I have basically put in an external electric field if you want. That's time dependent. So put in a frequency dependent electric field. Do some AC impedance on the system. And ask, how quickly can I oscillate the electric field and still have the response of the dipole to be adiabatic or not? Can these molecules orient on a time scale? Because I do now have time scales for everything. And so you could do some AC impedance spectroscopy, and you would hope that you could then recover some sort of effective equation out of this that says there's an effective dielectric, which is frequency dependent, that sort of responds to this charge that you're imposing in some sense. And so this would be relatively straightforward to do. I think I'm not going to do it because I don't want to think that hard right yet. But if that's something that people thought was a good place to start, then I think I could figure out how to do that. And so you've got a formula, you've got a formalism, you've got a way to include this sort of structure in here. And if you want to do PDE, you got a PDE to try and solve. So, okay, that was my goal, was to build at least one path from PDE and that people would recognize to problems that are being represented here. And I think this is maybe not the best, but an existence proof of a connection between math and things we want to discuss. Okay. And I do have, there's some references here, and I particularly want to draw attention. I didn't mention it before, but Roman's book is down here. Roman Shitkov's book has a very nice book on this as well. If you want to see a little bit more proofy, that's why I didn't use it, but very nice analysis of what's going on. And of course, Mauro Maggioni is doing some good related work on learning these kernels. So, okay, hopefully there'll be connections there as well. I'm going to end early. That's the best time to end.